Complex numbers. All complex numbers use this little fact here, that the number I is equal to the square root of -1. Now you've probably been told you can never take the square root of negative numbers, but that's if you're only working with real numbers. Now we're working with complex numbers. So if I equals the square root of -1, what does that make I squared? Well, I squared will be the square root of -1 squared, which is -1. How about I cubed? I cubed is I squared times I, which is -1 times I, which is -I. I to the fourth, that's I squared squared, which is -1 squared, which is 1. And I to the fifth is I to the fourth times I, which is 1 times I, which is I. And we're right back where we started. If you have to figure out what I to the 70th is, break it down into a power of I squared. Because I squared is -1, and since we're raising it to the odd power, it's going to be -1. Okay? Now, complex numbers are always in the form of a plus bi, where a and b are real numbers. So for example, 2, okay, I accidentally hit the pause button there, didn't mean to do that. So, back where we were, for example, 2 minus 7i is a complex number. Now believe it or not, every number you've ever worked with is also a complex number. For example, the number 100 is a complex number because it has a 0i tagging along. You just didn't know about that. Now we can do all of our normal operations with complex numbers that we can do with real numbers. I can add them. I just take the real parts, add them, and then take the imaginary parts and add them. So our final answer is 9 minus 2i. I add two complex numbers, I get a complex number answer. Subtraction works the same way. Subtract the two real parts and subtract the two imaginary parts. Multiplication is a little bit more complex, to coin a phrase. We're going to do FOIL on this. So I'm going to multiply my first terms together. So I'm going to get 6. I'm going to do my outside terms, 2i, do the inside terms, and finally do the last terms. And remember that I squared is -1. So what happens is we're going to get 6 minus 10i plus 4, and I get 10 minus 10i. So when we multiply, we get a complex number. Now, a special case of complex multiplication involves conjugates, when we have a plus bi times a minus bi. And remember that just multiplying real numbers in that form is called the difference of two squares. So for example, if I have x minus 3 times x plus 3, that's equal to x squared minus 9. I just square the two terms and then subtract. So we're going to do that with our conjugates here. So if I have a plus bi times a minus bi, that's going to give me a squared minus bi squared, and that's going to be a squared plus b squared. Can you see why? This is going to be b squared times I squared, and I squared is -1. Well, we're going to use that when we do division. So if I want to divide 3 plus I by 5 minus 3i, we don't like i's in the denominator. And so I'm going to multiply the top and the bottom by the conjugate of the denominator. In this case, 5 plus 3i. We're going to do FOIL on top, so I'm going to get 15, and then 9i, and then 5i, and then 3i squared. On the bottom, I'm going to get 25 plus 9 because of our little rule right there. So I combine similar terms on top. I've got a 15 minus a 3. I've got a 9i plus a 5i all over That's 34, isn't it? Yeah, 34. Now when we write complex numbers, we always split the real part and the imaginary part into separate parts. And we're going to reduce this. So I can take a 2 out of that. 6/17 plus 7/17 I. And that would be my final answer. Okay, so now that we can work with complex numbers, we can solve quadratic equations that previously had no real solution. So let's take a look at this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which is equal to 2 plus or minus the square root of 4 minus 60 over 6, which is equal to 2 plus or minus the square root of negative 56 over 6. And we don't have to worry about that negative 56 underneath the radical. We just make it I root 56. And that's your answer.